Okay, section 2.2, and we're looking at functions and mappings. Now, this is an odd little topic. By the time you hit the exam, you'll be used to the sort of questions that get asked, the way to answer them, certain sort of techniques. But before we get there, we need to stop and really think about functions and the way that functions work, and perhaps change our view of them a little bit. So if I say a function, if you haven't come across this chapter before, you're probably picturing something that looks like this, right? You've got an x-axis, you've got a y-axis, and you've got some sort of line or curve drawn on the axis, and that thing is the function, and we'd say y equals a function of x. Now, what we need to do is think about functions in a few different ways, right? So firstly, you could think of that function as a sort of, maybe you saw this back in year 7 or 8 when you first met algebra. Think of it as a sort of function machine, okay? So you take the x value as an input, and you put it into the machine and it spits out the y value. So let's say the function was the +2 function, right? So we'd write that as f of x equals x plus 2. Well, if I put in a 3, it spits out a 5. If I put in a -1, it spits out a 1. Okay, so if you put in an x, it spits out x plus 2, right? So we can think of it like that. So there's a sort of movement, isn't there, from input to output. And another way of thinking about a function is that you take all those inputs and all those outputs and you plot them on here. So the input for this point here, it's on the function because this distance here is the input and this distance here is the output. Okay, so you take all the inputs and outputs and you make them into a curved line like that. Another way of thinking about the function then is just inputs and outputs. So 3 and 5, -1 and 1. Oops. And it's a bunch of pairs, right? There's infinitely many pairs. There's the input first and the output second, and it's just a pairing up of these numbers with these numbers. Okay, so you get two numbers. It's important what order we put them in the brackets because the first number is the input, the second number is the output. But we could think of the function as not being this curved line, but as a sort of infinitely long list of pairs of numbers, and that's another perfectly good way of thinking about a function. Another way of thinking about it is this. We start off with a sort of a bag of stuff which we'll call a set. Okay, now a set in maths that's actually, a bag of stuff, a collection of things is about as good a definition as we're going to get, for the moment at least. And that in this case might be all the numbers, okay? So that set might be real numbers, but it could be anything. We've got a bunch of things, and then over here we've got another bunch of things which again could be the real numbers. And we take one thing from here and we join it up with one thing over here. You can think of that as a pairing up, like in the sort of coordinates way of writing it, or we can think of it as taking things from this set and sort of mapping them over to this set, sort of as though there's a sort of movement from one to the other. And that is another way of thinking about it. So this element here gets joined up with this element here. This element here gets joined up with this element here. Okay? Now, in maths, if we're looking at functions, as in maths A level, these functions are often going to be starting with numbers and ending with numbers. So if I take a function that I can write with an algebraic expression, like f of x equals x plus 2, then we're saying that the numbers in the starting set are, the things in the starting set have to be numbers, and the things in the finishing set have to be numbers as well. But in order for it to be a function, it doesn't have to be that way. So I could have a set, here we go, in this set I've got a triangle, a square and a circle, and I'm going to say, let's have a different example. Let's have a triangle, a square and a pentagon, and say triangle maps to 3, square maps to 4, pentagon maps to 5. And there's a rule behind this function, isn't there? And the rule is just count the number of sides. So your inputs now are shapes, your outputs are numbers, and that's a perfectly good function. We've got a set of things which are our inputs, we've got a set of things which are our outputs. And we've got a way of getting from the input to the output. Now here's another function. I've got a set of things. I'm going to say that, and that. And that number there maps to 4. That thing there maps to 4. This thing here maps to that shape there, and this thing here maps to a circle. Okay? Now, I'm giving this example to really sort of get the idea here. This set, previously we thought of the set as being either the numbers or shapes, what about having a set which is just three things? A set is just a collection of things. So I've made up a set here, and it's made up of these three objects. I can have a function on this set, and that is, if I input this, the output is the number 4. If I input this, the output is that squiggle there. If I input this, the output is a circle. So I have a function. I have a pairing up of things from my input set with things from my output set, and that's fine. It's not a very interesting function because there's only 3 elements in the set that I start with and 3 things in the set that I finish off with, but it's still a mapping, it's still a pairing up. I couldn't possibly plot this function on a graph as a curve because, you know, how do I put these 3 objects on a x-axis? I can't do, but this is still a function, okay? So our old picture of a function, x and y-axis with a curve, our new picture of a function, inputs, outputs, join up the inputs with the outputs, okay? Now, there are a few other bits and bobs that we need to know. So, if you have this model where one input gives you one output, one input gives you one output, then that's called a one-to-one function, okay? If you have, inputs, outputs. If you have this model where you have somewhere in there are 2 inputs that give you the same output. Now that only has to happen once. Everything else can be one input gives you one output. But if just once you get 2 inputs that give you the same output, that is called a many-to-one function, okay? And it doesn't have to be 2 inputs, it could be 3 inputs or 4 inputs to give you the same output, but it only has to happen once for it to be called a many-to-one, not a one-to-one function anymore. And the typical example of that is y equals x squared, okay? Or f of x equals x squared. 2 squared is 4, minus 2 squared is also 4. So you've got 2 inputs that give you the same output, okay? That's the one that we're used to seeing a lot. What about this though? Can we have one input that gives us 2 outputs? And the answer is that is not a function. So y equals positive or negative square root of x is not a function. And the reason is that with a function, we just decided in order for it to be called a function, if I give you an input, you have to know what the output is, okay? If I give you an output, you don't necessarily have to know what the input was. So if I say the output was 4 and the function was y equals x squared, what did I put in? Was it 2? Was it minus 2? I don't know. That's okay. We're still going to allow that as a function. But this way around, we're not happy with it. We're not going to say, okay, the input is 4. What's the output? It could be 2 or minus 2. I'm not happy with that. If we're going to call it a function, we're going to have to say, give me an input and I can tell you the output. So what if we just said the positive square root of x, then the square root of 4 would be 2. And that would now be a function because this bit wouldn't exist, okay? So we can have a many-to-one function. We can't have a one-to-many function. We're just going to say that's not a function, okay? Now, this set here is called the domain. Now, I've been avoiding the words domain, and this set over here is called a range. I've been avoiding the words domain and range for a little while, and here's why. The input set is called the domain, the output set is called the range. So domain is basically x values, range is basically y values. Except, if I take a function like, well, let's go back to the y equals x squared, right? The domain, in this case, I haven't said what the domain is. So strictly speaking, I haven't actually finished defining this function. I haven't told you what the inputs are. Now, if I write y equals x squared, we will assume, or if I write f of x equals x squared, we will make the assumption that the domain is the biggest possible domain, right? So we will make the assumption that x here is a member of, if you've not met this, it's a contained in symbol. If you've not met this, it's an R for the real numbers. So we'll make the assumption that x is a real number, okay? And if that's the case, then I can input anything on the whole real number line. What's the range then? Well, the range now, if you take numbers and squared them, you're going to end up with positive numbers, or well, 0 or positive numbers. So for this function here, the range is that y has to be a number and greater than or equal to 0. Okay, so that is my range. So sometimes we picture these things as being real numbers here and real numbers to here, and these real numbers get mapped to some of these real numbers, and if there are numbers over here that don't get mapped to, then that's fine, that doesn't matter. Well, strictly speaking, the domain is only the set of things that get mapped, and the range is only the set of things which get hit, okay? So if we're looking at this function, this range is not real numbers, this range is positive real numbers. Now, it's sometimes helpful to picture having real numbers here and real numbers here, and let's say I'm taking this function x squared, so, 2 squares and gets 4, minus 2 squares and gets 4 as well, 3 squares and gets 9, but somewhere in this bag over here is a minus 4, which just never gets mapped to, and somewhere over here in this bag is a minus 3, which never gets mapped to, okay? Now, strictly speaking, if we're picturing it like that, this is not the range anymore, this is a set which contains the range, okay? It's fine to picture both things, but when it comes to actually being strict about domain and range, the domain is the set of things which can get put into the function. The range is the things which can get output. Now, also strictly speaking, if I just say f of x equals x squared, I haven't defined the function. I need to tell you the domain as well. So here's another function, f of x equals x squared. X is a real number which is bigger than 4. Now these two functions here are different functions because the things that I'm putting in this function are different to the things that I'm putting in this function. Now in practice, we'll often just write f of x equals x squared even from now on, and we will assume that the inputs are the biggest possibles, okay? But we have to be a little bit careful with it. So for example, f of x equals 1 over x. If I just write that on its own, what's the domain? Well, the domain would be x is obviously numbers, but I can't put a 0 into this function. So x is not equal to 0, okay? Because if you do 1 divided by 0, that's undefined, that's not something we can do. So that is a function. If I cover that bit up, strictly speaking, I've got a problem. What is your domain here? If I've not given you a domain specifically, I will assume that this is the domain, okay? On the other hand, I can define this function and say, well, x is a real number and x is only numbers less than minus 4, for example, and that is now a different function because it has the same algebraic bit, it has the same way of getting from inputs to outputs, but I've changed the inputs. And if I change the inputs, I'm obviously going to change the outputs as well. If I change the domain, then the range is going to be affected. So it's a bit fiddly because we can make a big fuss about a function needs to be defined with the expression and the domain sort of stated, but then when we're not dealing with functions specifically, we'll just make assumptions about the domain is kind of what we think it is. It's also fiddly because the domain should be the inputs and the range should be the outputs, but we often talk about the domain set as being, sometimes we're a bit not careful enough with what we mean by the domain and the range. And we say the range is the y-axis, but when we get asked specific questions, we need to remember exactly what our definition is. The range is the values of y which the function takes. Now, we're nearly there. We're nearly at the point where you can play with exercise 2b, but let's just say this. So what if I wanted to say, okay, here is the real numbers and here is the real numbers, and I have a mapping which takes x to the square root of x. Well, this isn't a function, and the inputs can't be negative numbers. So how do I describe this thing? Well, if we just use the word mapping, that'll sort of get us out of all trouble. So, a mapping is to take some things from a set to some things from another set, and it can be many to one, it can be one to many, it can take everything from this set, it can not take everything from this set, but mapping is the word that we will use to represent that thing. So if you look at example 7, when it's saying, are the following things, what are the following mappings functions? Are they one-to-one, many-to-one, or whatever? We can't talk about a one-to-many function, but we can talk about a one-to-many mapping. All right, so that's mapping is the word that'll get us out of that problem. So this one, for example, is a one-to-many mapping, so it can't be a function because one input needs one output if you've got a function. This one here is a one-to-one function. If you put one x value in, you get one y value out. This one here is a one-to-one mapping Is it a function? Well, we could say it's not a function because the domain is supposed to be the x-axis, and there's a value on the x-axis which doesn't have an output. Or we could say it's a function if you define the domain to be the x-axis not counting 0. Okay, and then on D, yes, it is a function. It's a many-to-one function because there are two different values that if we input them, we get one y value out. The domain of it is all the x-axis, and the range of it is all y values bigger than that particular number there. Okay. I know there's a lot of information here. We're nearly there. Let's keep going. And again, it will be nicer when you actually finally have practiced this and get to the exam. It will seem more straightforward than it perhaps does at first. Let's just check this. The new exam board, on their specification material at least, have asked for answers for domains and ranges in set notation. Now, previously, on the pre-2017 syllabus, they didn't mind too much about the set notation. Now they've specifically said in the mark scheme in set notation. I don't know how harshly they're going to mark that, but we better make sure we know what we mean. So set notation, here's a squiggly bracket. That means I'm about to define a set. So this is the set of things that we call x, and those things are 1 or 2 or 3 or 4. So you can think of that as a set with 1, 2, 3 and 4, and there's nothing else in it. Okay, then we close the brackets. I could have something like this. Here is a set. The things in the set, we're going to call them x, and they are real numbers. So x is contained in the real numbers means x is a number. X is a thing on the number line. That's it. There's a set. That is all things on the number line. Here's another set. X is things on the number line, and we just put a comma for the end. Minus 5 is less than or equal to x, less than or equal to 5. So this set here is the whole x-axis. This set here goes from minus 5 to 5, including the minus 5, including the 5, and all the numbers in between. Okay? So the set notation is just that. You need to know this containing symbol. You need to know this R for all real numbers. You need to know the squiggly brackets for here is this, I'm about to start defining a set. If in doubt, put your answer and put it in squiggly brackets, and that might well be enough. But take advice from your teachers, look at the mark schemes when we have a few more past papers to see exactly what conventions the exam board are going to follow when they allocate the marks to those questions. If we know R, it might be helpful to know these symbols. N means natural numbers, so 1, 2, 3, 4, 5 and so on. Sometimes people call that 0, 1, 2, 3, 4, 5 and so on. Z means integers, so positive and negative whole numbers and 0. Q means rational numbers, so everything that can be written as a fraction. Q from quotient, right? Because a fraction is one number divided by another, quotient meaning a division. And those are the ones that we're likely to use on the A-level course, all right? Very last thing, and we're finally done with this complicated section, and you can play around with the exercise. One thing I should throw in is sketch the graph. Again, sketch the graph. If you have a function and you want to know what the domain and the range are, well, sketch the graph and look at it. What values of x get put into the function? What values of y get hit? So if you've got a parabola, none of these y values down here are getting used by the function. So the range of that parabola is this number and upwards, okay? And then you can think, oh, well, how do I find the turning point of parabola? And maybe use calculus, maybe use completing the square, whatever, all right? If you've got a function, so let's take as, I don't know, let's say the function looks like this, but you're told that the domain is just x equals 3 or more, then the range, well, we ignore all this, the range is this y value and higher than that, isn't it? Okay, so sketch the graph. If the domain is restricted, that will change your range. A graph sketch will help you to see what the range is. Last little bit is just that there is an extra bit of notation. We're used to saying f of x equals, I don't know, f of x equals x plus 2. We can write this as f is the function which takes x to x plus 2. Those two notations mean exactly the same thing. And we can also have a multi-part function like this. So I can say f is the function which takes x to, and I'm just taking the example from the book here, if x is less than 1, it takes x to this value. If x is 1 or bigger, it takes x to this value. So you don't just have to have one algebraic expression to take your input to your output. You can have different ways of doing it for different x values, but if the domain is the real numbers, everything in the real numbers gets mapped to something. So everything from the domain gets taken to the range, and you can work out what the range is by sketching a graph. And I won't label that point anymore because it's on page 30 for those people that want to check that one out. Okay, we've finally got through all the fiddly bits of thinking about functions in this new way. From here on in, I think this chapter gets a little bit easier.